Good afternoon or good morning, depending on what time zone you're in. Today we're going to talk about modeling mechanically joined fasteners. We're going to talk about fastener stiffness, modeling options for creating fasteners inside FEMAP, and using Simcenter Nastrend's fastener features. Talk about how the presence of fasteners can affect your mesh and the choice of elements you use. Talk about some of the ways you can create fastener elements inside FEMAP, and then I'll do a brief demonstration. So mechanically fastened joints are essentially found in almost any structure. They can be in the form of rivets, bolts, high locks, and so forth. Basically, anytime you have to connect two pieces together, you can either bond them, weld them, or mechanically fasten them. And so having mechanical fasteners is kind of key to any structural analysis. Analyzing fasteners, though, for stress in a finite element model is generally considered to be impractical. Why? Because there's just so much going on that in order to capture enough detail in your model to actually predict stresses, you'd have to have a very complex model, which is just not practical if you have dozens, hundreds, or even thousands of fasteners. So effects like friction, contact, bending of the fasteners, preload of the fasteners, all those sorts of effects are very difficult to accurately model on a large scale. I have seen people, of course, create detailed models of a single fastener using solid elements that include the head of the fastener, the washer, the nut, and so forth. You can do that for an individual fastener by all means, but trying to do that, as I said, on a large scale is generally not practical. So usually our objective is to find out what the forces are in the fasteners and then use other methods then to predict whether the structure is strong enough. Most load in a threaded fastener joint is typically transmitted through friction. So you get that clamp up force from your bolt torque holding your two sheets together tightly enough that load gets transferred through friction. Most of the time when we analyze that, though, we ignore that effect. Why? Because it's hard to predict in advance and it's conservative to ignore it. And so we'll generally use a simplified representation of the fastener that doesn't include any of these friction effects. And then once we do that, then we can go calculate our margins. There's a lot of different ways to go about doing this. I'm not endorsing any one method today. I'm just going to try and show you some of the available methods. One of the advantages of working for a company like Saratech is since we do analysis for many customers and we provide technical support for many customers, we have kind of a unique opportunity to see how a large number of organizations analyzes their joints. And when we do analysis for customers, we generally try to adopt whatever method they prefer to use. So you can think of a multi-row joint as being really a network of springs. We've got these members in tension, and our fasteners are put into shear when we pull on them. And you want to get the loads that are being transferred through each fastener. And in order to do that, you have to know what its effective stiffness is. In the simplest case, you can assume it's rigid or nearly rigid. And this is a pretty good approach for simple joints that maybe have a single row of fasteners. Since there's really only one load path through a single row of fasteners through that one row, the relative stiffnesses of the different members doesn't really affect the load distribution a whole lot. Basically, all the load has to go through that row of fasteners. So it's almost something you can predict in advance. But as soon as you get into more complicated multi-row fasteners or more complicated loading or fastener patterns, then the fastener stiffness starts to become potentially significant and the load transfer through each fastener. Now, coming up with what the stiffness should be is very complicated. Why? Because it's a surprisingly complicated mechanism. We have the fastener itself bending and shearing, and it's being supported by the edges of the hole. And it also has some fixity on the head and at the nut that depends on how large the head and the nut are, how tightly they're torqued, and so forth. So trying to predict in advance what that stiffness is something that you can probably find dozens and dozens of papers on. There's lots of people have tried to come up with a method for predicting what this effective fastener stiffness will be. So there are several semi-empirical methods for doing this. that take into account factors like fastener length, diameter, materials, and so forth. They include equations you'll see used in industry: Huth, Swift, Tate and Rosenfeld. A common one is developed by Ruttman, combined with a couple of other people. And then just about every aerospace company has their own internal method that they've used, sometimes several methods they've used internally. I think the fact that there are so many different methods kind of tells you that there is no one method that is clearly the answer. If there was, then probably everyone would be using it. And in reality, there doesn't seem to be any sort of unanimous consent at least amongst Saratech customers, as to what the best method is. So we see pretty much all sorts of methods. Huth is probably the simplest, and Ruttman's actually fairly complicated. It actually involves multiple element types, trying to capture all of those separate effects that we talked about for fastener stiffness. So I'm not trying to endorse any one or the other, but I am going to show you an example using Huth just because it is simple and common. So the Huth equation looks something like this, and you can see it has all the things you would expect it would have. The thicknesses of the members you're connecting together, the diameter of the fastener, the moduli of all the materials involved, and so forth. It also has some parameters that represent whether it's a metallic or composite structure, and whether it's in single shear or double shear. So an example, there's the original paper, if any of you want to go read it in German. So as an example here, if I have a single shear joint with 3 rows of 3/16 inch A286 fasteners with 080 thick aluminum, then these would be the inputs for the Huth equation, and I would get a stiffness that looks something like this. So now I've got that stiffness, what do I do with it? Well, I'm going to create elements inside my finite element model to represent my fasteners. And there's a wide variety of elements you can choose. Again, there is no really right element or wrong element. And in fact, some elements you may use, say, in preliminary design, and some elements you may use doing more detailed analysis, because the fidelity you want to add increases as your design evolves. So common elements are the rigid element, the RBE2 or R bar, the bush spring element, C bush. Nastran has a fastener element called the CFAST, and then a lot of people will model it with a beam or a bar, C beam or C bar. And as I said, some people will use combinations of multiple elements to represent different aspects of the fastener behavior. And then when it comes time to actually create the mesh that this fastener element will attach to, you have some options as well. For example, you can create a mesh that is independent of the fastener location. You just create a mesh and then you attach your fasteners after the fact. Or you can make sure that your mesh has a node at the specific fastener location predefined that you simply can connect. And then some people prefer to actually have the holes represented in the mesh. So if we're going to use RBE2 elements, rigid elements, they're very simple. There's no stiffness to calculate. And it's usually fairly conservative to do this because the fact that everything essentially has an infinite stiffness means that one fastener is likely to pick up more load than it would in reality. Because you don't have that compliance in there, basically the first fastener that sees the load is going to try and grab it all. But this is possibly too conservative. And it also has some other disadvantages. One, it's a bit harder to recover loads. You need to go look at the MPC forces. You can't just look at element forces. And because there's no element coordinate system associated with this, it can be difficult to resolve which loads are axial and which loads are shear. You can't simply say, give me the axial load in my R bar or my RBE2. It doesn't really exist. So what you end up with is forces and a coordinate system that you may then have to rotate into the coordinate system that lines up with the axis of your fastener. So they're a little bit cumbersome in that sense. You can also use the C-bush elements, which are the beam elements. And these things are nice because they let you actually define stiffness for all 6 degrees of freedom. So you can use that Huth equation or an equation of your choice, calculate your stiffness, and directly define it on the property for the C-bush. Generally, when you do this, you assume the axial stiffness and rotational stiffnesses are large. You're assuming that your two members are attached together in such a way that when they rotate together. There's enough clamp up to hold them together. So you want to have no relative bending between them. And so you'll want to have a large bending stiffness for your bushes. If you actually have a zero length, if you have the two ends of your fastener coincident with each other, which you can do, that complicates life because now you lose that axial element coordinate system. So it's nice to have a little separation at a minimum between the two nodes so that you can resolve an axial load from the shear loads. The next element you can choose from is the CFAST element. And the CFAST elements are unique, and I don't think a lot of people really use them, even though they can be very helpful. Essentially, they're springs, just like the C-bush. But instead of connecting two nodes together, they're actually used to attach patches together. What is a patch? Well, a patch is a group of elements that are defined either by element IDs or by property IDs. So a patch could be a single element or it could be multiple elements. What Nastran actually does internally is it figures out where your fastener element should be in space, projects that location out onto the element patches, and then it creates a node internally, automatically, node that you don't see. Then it connects that node out to the nodes of the patches using an RBE3 or MPC, or RBE3 like MPC element to connect it up. So what happens is you don't really have to know where your fastener is in advance when you create your mesh. Nastran will take care of attaching it for you regardless of the mesh location. And this is helpful if you have a preliminary design situation where maybe you don't even know what your fastener pattern is going to look like. And you don't want to have to keep remeshing every time you try a different fastener pattern. It's also helpful if you have hundreds or even thousands of fasteners. So rather than trying to manage hundreds or thousands of fasteners, there are some tools where you just keep a table of the fastener location. And once you give Nastran the fastener location and what the stiffness is of the fastener, Nastran takes care of everything else. So it can be very helpful in situations like that. If you want to define a CFAST element inside FEMAP, you have to give it a property. You'll notice here that the property includes a diameter and a mass. You can provide some damping. And then the stiffnesses for the 6 degrees of freedom. Now, the diameter is used not to calculate the stiffness. It's simply used for Nastran to figure out whether the element overlaps multiple, or the fastener element overlaps multiple shell elements. So if you have a very fine mesh that's smaller than the diameter of your fastener, it may actually then attach to multiple elements. If the diameter is smaller than the element size, then it's going to pick one element and attach it. You saw in the earlier figure. And then there are different ways of specifying how you're going to attach them together. The top one there, unfortunately, only works if you're doing what's called a spot weld, where you can actually attach it to nodes. If you're talking fasteners, you can only attach it to patches, which can either be with an element ID or with a property ID, in which case all of the elements of that given property could potentially be connected by this fastener. And then finally, there's the C-beam elements. Now, some people love C-beam elements for fasteners. As I mentioned, the Rootman method is kind of dependent on using beam elements. But it's kind of complicated to create the appropriate properties, and in reality, fasteners don't really behave like beams. So the best approximation if you want to use beams is to use a high bending stiffness so that you can enforce that your two members bend together, and then use the stiffness factors on the beam properties to adjust the shear to get the correct stiffness. One of the advantages of beam elements, which is why a lot of people use them, is because it can also include bolt preload. So if you want to include the effect of preload and the bolt torque on your model, then the beam is the only way to do that. And so you can connect these things together directly to nodes, or you can use what we call a spider web. And I will demonstrate that later. But a spider web is simply a method of connecting all the nodes on the boundary of your hole together to a single node that you can then hook up your fastener element. FEMAP actually provides an API called hole-to-hole fastener to automate this whole process. So it will actually create the spider web in the hole for you, create spider web in the opposite hole, and then connect them together with a beam element, all more or less automatically for you. As I mentioned, you want to adjust the shear area to get the correct stiffness, and that's what this shear area factor is you see here on the beam property. And a bar works very similar. Generally, people use beams because they have a lot of other features that you can potentially use, but a bar is a bit simpler and has the same basic feature here. So if you're not using CFAST elements, you need to mesh your model in such a way that you have a means of attaching your fastener elements to it. So the first question you have to ask yourself is, do I want to include the holes or do I want to eliminate the fastener holes? Because generally we get our geometry these days in glorious solid 3D CAD, and it's got every little detail, including the fastener holes, even a chamfer if it's countersunk. But once we've reduced this down to shells, we just end up with basically a simple hole. And if we keep that hole there, then you're keeping your idealized geometry a little bit closer to the actual geometry. And it's very easy to see your fastener location and size. Wherever there's a hole, you probably have a fastener. If it's a big hole, it's a big fastener. If it's a small hole, it's a small fastener. So it's kind of convenient just for visualization to have those holes there. But unless your mesh is fairly fine compared to your hole size, you're just going to end up with a messy mesh around those holes, right? Probably if it's a relatively coarse mesh compared to the fastener size, you may just end up a little triangular hole there. It's not even going to be a nice round hole. So in that case, it's really probably not buying you a whole lot. You're better off just removing the hole. Now remember, we're not trying to get stresses. And if we leave that hole in there, someone might say, well, having the hole there is a good idea because that way I get the effect of the hole and the stresses. But we're kind of fooling ourselves if we think we can put a fastener element in there and get any sort of realistic stress around the hole, right? Because we don't have all of those things like contact, and friction, and clamp up, and head fixing. None of that is actually in the model. So even with the hole there, it's not really going to help us get good stresses. Again, all we're really after is stiffnesses, so we can get the loads. Removing the holes, though, does require some effort. It's an extra step. And it's once you've eliminated it, what you're left with is a bunch of nodes, and it's pretty easy to forget to attach those nodes together with the fastener. So you may find that you've left a fastener out of your model, which could have some complications. But the meshing toolbox in FEMAP can automatically eliminate holes and create a mesh point at the location, and you can also manually create mesh points to control where these nodes go for your fasteners. So there are some convenience features in FEMAP that will demonstrate to keep track of these nodes and make sure that you get a node where you want it. And the way that works is with the meshing toolbox feature. We can go in and we can either add a surface mesh point if we didn't start with the hole, but we want to make sure that we have a node there for our fastener, or when we remove the hole, we can actually check the box here and say add surface mesh point, and when it eliminates the hole, it will put a mesh point at the center where the hole had been. And then you also have the mesh point editor tool, which would let you actually import these fastener locations from, say, an Excel spreadsheet. So if you have a separate spreadsheet you're using to track all of your elements, then you can use this as well to ensure that you get a node where every fastener should be. So I mentioned wagon wheels and spiders, which are essentially alternate names for the same thing. And what it is it's an RBE2 or RBE3 that fills the hole in the mesh and connects all the nodes on its perimeter to a single node at the center that you can then attach. And there are actually 4 different API functions to do this: spider curve, spider node, spider surfaces, and then just plain old spider. And so you can somewhat automate creating these things fairly quickly. There's several different variations here. I think the one based on curves is probably the easiest, because you just pick the curves that make up the perimeter of your fastener hole, and it takes it from there. But one thing you have to be careful about here is it's not really creating a node at the center, quite honestly. What it's doing is it's just averaging the locations of the nodes. So if you don't have a uniform mesh around the hole, you're not necessarily going to get a node at the center. In addition to this API, when you create a rigid element in RB2, RB3, it also gives you the option to create a node at the center. So you can either do it with the API, or you can just use the built-in function for creating rigid elements. I think this one's a little bit easier just because you don't have to pick the nodes, you can just pick the curves. Another thing we see amongst the customers at Saratech is element length for our fasteners. And there's 2 schools of thought here. One is you leave the nodes separate. So your fastener element actually has a discrete length to it. A lot of people don't like that though, because you're basically cranking a moment in to your structure due to the fact that you have separation. So what they'll do is they'll put the nodes together to eliminate that moment. Now, that putting the nodes together may prevent that moment, but it complicates some things. One is you can't use a beam element at that point because you can't have a zero-length beam. If you're using bush elements, you no longer have an axial coordinate system unless you explicitly create a coordinate system for your fasteners, which may potentially require creating separate coordinate systems for hundreds of fasteners, which is probably not going to be very practical. And you actually have to go start moving geometry around, which can cause some other problems and create its own unrealistic moments. And in reality, at least for single shoe joints, that eccentricity is real. So the fact that there is a length or a physical separation does actually cause an eccentricity, which you will lose if you put these 2 members together and have a zero-length element. In reality, the fact that it's bending is going to cause some local bending stresses here, but that's probably not a problem because, again, we're not really paying much attention to stresses. So in theory, at least, as long as it doesn't affect the load being transferred in the fastener, having some length here is not necessarily a bad thing. But I'll leave it to you to decide the best way to model it for your structure. Whether you include holes or remove holes, careful grouping of the nodes and elements will reduce error and save time. Fasteners are frankly complicated. You can't just mesh them in an automated fashion. You just can't push a button and create fasteners. You can have hundreds and thousands of them, and they can all have different stiffnesses. If they're different diameters going through different thicknesses of material, you may end up with dozens of separate properties for them, even amongst fasteners that all have the same diameter, because the differences in the materials they're going through and the thicknesses, they could have many different properties. So it's a good idea to create groups of nodes that are connected by fasteners for each part, as well as groups of fastener elements by their fastener type and diameter, so that once you've created all of your fastener elements and you want to easily go in and extract their loads, go off and do your strength calculations with them. If you have organized everything very carefully, your chances of leaving out fasteners are greatly reduced, and your post-processing time for extracting the loads will probably be much better. So organizing everything very carefully with groups or even layers, I tend to prefer groups, will pay dividends later. So let's talk a little bit about creating these elements. So I said there's no automated way to create fastener elements. In reality, that's not entirely true. TMAP has a way to generate connections, what they call connection generation. And it does this based on giving it 2 lists of nodes. And what it does is it sorts through these 2 lists of nodes and pairs them up based on their proximity. So we'll figure out which node in list B is closest to a given node in list A. And then once it finds that pair, it will connect them up using a variety of different types of elements that you can specify. So you can use just a plain MPC to connect them. You can create an RBE2 between them. You can use a C-last spring or a C-bush spring to connect them, or you can use beams or gaps. So you have many different ways of attaching pairs of nodes together in a more or less automated fashion. The only problem is it can't do CFAST elements, unfortunately, because CFAST elements are not based on nodes, they're based on elements. Okay. Let's see. I mentioned the spiderweb of API, so there are some other ones. There's the hole-to-hole fastener, which I said earlier will actually create 2 wagon wheels for you automatically, 2 spiderwebs automatically, and connect them up with a beam element in one operation, which is nice. There's also a weld and fastener element generator, which will generate CFAST elements or the similar C-weld elements based on Excel or data surface input. And then there's something that actually then goes in and checks your CFAST and C-welds to make sure that you've attached them appropriately. You didn't create some point in space to find a fastener there, and then it's just not possible to connect from that back to the elements. So it'll actually go through and make sure that your fastener locations make sense given your mesh. So these APIs are out there. Now, in reality, just about every large company that does a lot of fastener analysis has their own APIs to do this. Why? Because, as I said, it's kind of complicated. There's lots of different ways to do it. So what people will do is they'll write an API to automate the process. And the advantage of that is that then gives them repeatability. Basically, anyone in the organization will create fastener elements the same way. They'll calculate their stiffnesses the same way because it's all effectively been automated by this API. So it's a good idea to create the API, not only because it speeds things up a lot, but also because it ensures consistency from analyst to analyst. So just about every large company that does a lot of fasteners that I've encountered has some sort of API to do this already. And for things like the Ruttman fastener, which is relatively complicated, automating it makes your life a lot easier because it involves multiple elements, multiple RBEs, springs, beams, all mixed together. So creating that by hand is actually fairly time consuming, but it can be automated with an API very quickly. I mentioned bolt preloads. So you can include contact between members and then apply a preload. This gives you a better load distribution from contact and allows you to include that preload in calculations. You can look at things like separation, things like that, and what the axial load is if you're talking about a fastener and tension. And unfortunately, it's only supported for bolts with bar beam and solid elements. It doesn't work with bushes or CFAST, which tends to drive everyone to using a bar or a beam for a lot of these things if they're doing a fastener preload. Solid really doesn't make much sense unless you explicitly modeling a fastener with solid elements, which generally doesn't happen on a large scale. And the way the preload works is it gets treated as an initial subcase, so it's going to enforce a strain on the bolt elements until you get the required preload, until you actually pull things together and generate the axial load you expect to. Okay, any questions so far? Should I launch into the demonstration? Okay, so the demonstration, we're going to remove holes and mesh it. We're going to add wagon wheels in cases where we leave the holes, and then we're going to connect it together with this variety of different elements. So I have 4 simple joints, and we're going to go in and mesh these model of fasteners using those different fastener types. So first thing I'm going to do is I'm going to go into the meshing toolbox, and I'm going to eliminate the holes from 3 of these. So I can go to vertical here so I can easily pick them. I'll go to feature removal. I'm going to make sure that I turn that on so I get a mesh point. Now the limit size will actually let you specify a criterion for the hole, in which case it will go in and eliminate them automatically. I'm going to go ahead and eliminate them manually. Select these. and they're gone. But you see it left the mesh point behind for me. So that when I mesh these now, I should get a nice mesh that includes a node at that location. Oh, let's see, it's a good size. Let's try one, see how that goes. We'll find. Let's try it. Let's not get carried away here. That's a little better. So you can see it's left the nodes, even though it had to tweak the mesh a little bit. It put nodes exactly where my fasteners are. Now this one though, I'm going to go ahead and mesh it. And I'm going to leave the holes. Okay. Now I'll go ahead and put a wagon wheel. So as I said, you can go to custom tools and there's a feature for that, an API for that. Under meshing, spider curves. It's going to pop up with an option here. Say, okay, there's my wagon wheel with a node in the center. Repeat that each hole. And I'm done. Now, a couple of comments. One is, and actually we talked to the developers about this and they said they're going to work on it. Once you've created nodes with mesh points, it would be really nice if I could just go select those nodes automatically based on the fact that they're associated with mesh points. And in fact, I can put mesh points in groups even by one. The problem is that as far as I know, and the developers kind of confirmed this for me, there is no way to get nodes that are associated with mesh points. Now that I have an API that I was sent that does that, but it's an API. So there is no built-in way in FEMAP. But recognizing that that would be kind of helpful, they said that they'll work on that, try and add that to FEMAP. So that's why I said earlier, probably you want to try and keep track of things with groups if you can, so that you don't have to figure out which nodes are which. And so if you look, you'll see I've got some groups predefined that I could then go in and add fasteners to and so forth, and put specific nodes in that would make things easier. But since these are relatively small models, I don't really have to worry about that so much. So now what I want to do is I'm going to connect these up with rigid elements. So I'm going to go to, this is a little confusing. You would think, oh, you would go to connect, but connect is only really for doing these connection regions. It's not for actually creating fastener elements necessarily. So what you want to do is go to the connect that's under the mesh instead. We're going to select closest link, and I'm going to pick the nodes that are associated with these mesh seeds, or mesh points. Then I'm going to come down here and I'm going to grab the next group nodes on the other member. Say OK, and then you can see now it gives me an option here, and I say, okay, I want to use rigid elements. I'm going to connect all degrees of freedom. Say OK. Now you can see there I've got some rigid elements in there to represent my fasteners. So it's pretty much as simple as that. And you can imagine if I put those nodes into groups already, then when I went to select them, I wouldn't actually have to click on, because you could potentially have 100 fasteners. I wouldn't pick on 100 nodes. I would already have them in a group, and I would just select it based on the group. So you could do it even faster as long as you have things organized by groups. And of course, I can do the same thing. This time, I can do it with modeling bush elements. So again, mesh, connect, closest link. For those of you who are experienced FEMAP users, you're probably already familiar with this functionality. So this is probably, oh, I didn't do that, quite boring. 3 groups. probably pretty boring. So I apologize in advance if you're all experienced FreeMap users. Okay, but this time I'm going to use line elements, meaning I'm going to pick my bush, have to give it a node or a vector to define its local element coordinate system. I use the default here. Say OK. Again, now I've got bush elements in there. Let me go ahead and just turn off the show elements real quick. Fortunately, I forgot to define properties. I got plot planar elements. But anyway, turn off the geometry. There you go. So now you can see those bush elements. You can see our rigid elements. So the next thing we're going to do is fastener elements, the CFAST. The CFAST, as I said earlier, is based on the location, and then you're connecting actually elements together. So it's a little bit of a strange beast. So in reality, I have mesh points here because I wanted to keep track of where my fasteners are in space. But there's really no requirement that these mesh points actually be located, or these nodes be located at the same location as the fasteners. Again, the beauty of the CFAST is the fact that it lets you decouple your fastener location from your mesh. And you can basically put a fastener anywhere without having to change your mesh to reflect that. But for the purposes of this demonstration, I'm going to go ahead and leave that node there. And so we're going to go in to element, create a fastener element. And now a spot weld element, a weld element is basically the same thing, except you don't specify the stiffnesses. It calculates it for you based on the diameter. So that's really not generally what we want for fasteners. We want to stick to fasteners as much as possible. CFAST. You can see these are the options, but some of these options only really apply to the spot weld. It's really only the last two that we can use. So now I'm going to start connecting fasteners together, and then it also wants to know our elements together, but also wants to know where the fastener should be in space, which could just be an XYZ location, or I can pick it based on a node. So let's see here. Let me grab that one. Grab directly below it, without having to rotate it. Sorry. Should be that one there. There we go. Those are lined up. Yeah. So I'm going to connect those two up, and I need to define the location. So again, I'm going to do it based on a node. But this could just be an XYZ location if I wanted to. Say OK. And so you'll see what it's done is, first off, based on the diameter associated with this, it actually drew a little cylinder here, so I can see what the outline of the fastener would be in space. And then it gave me some lines that showed me which elements were attached together. Looks like I might have grabbed the wrong element. That's okay. Gives you the idea. So those lines represent basically the RBE3 that it's created on, or well, that Nastran's going to create automatically to connect these elements together. Okay, so I can repeat that process for the other ones. Better job. There we go. That's better. So my fastener location is here. So again, it's showing me the RBE3, showing me the outline. I can see the extent of the fastener. Okay, so that's my three elements. So now let's try the beam approach. So I've predefined these properties. You can see here. So I filled in some stiffnesses already for my CFAST for shear stiffness based on the Huth calculation I showed you earlier. The beam is a bit more complicated because then I had to take its stiffness and then based on the modulus of the material, in this case steel, its length, I then had to calculate what the shear stiffness would be based on just the shear modulus and the area and the length. And then I had to define the shear area factor here to make sure that I got the correct stiffness. So some additional calculations are required above me on calculating stiffness in order to use the beam, which is why I said generally I think beams are more trouble than worth, unless you are doing bolt forces. But you can do it. And then the bush is obviously very straightforward too, just like the CFAST I was defining some shear stiffnesses, and I was off and running. Okay, so let me go ahead and create those beams. Again, I can use this mesh connect feature to generate my beams for me more or less automatically. Just need to pick the nodes. Again, this would be easier if I had these things pre-grouped because then I can just select the group here. Since I only have a handful of nodes, this is easy enough. This time I'm telling you I see beam. Still have to give it a location as I did before. Again, I'm going to use the default. Say, okay, here's my beam elements. So those are how you would create fasteners, either using holes or not using holes, or using each of those 4 different types of elements for creating fasteners. Any questions so far? So if I did this and I went and ran it, you'd get results that look something like this. And you can see there are some slight variations in the results, but not really enough to worry about. They're effectively, this mesh had actually turned out a little differently because I've got the holes. So there's some differences just due to the mesh. But by and large, any of these methods will give you effectively the same set of results. So it just depends on what's most convenient to you and what you think makes the most sense given your structure. Okay, I've been talking for almost 45 minutes. If there aren't any other questions, that completes today's presentation.
So we do have 3 questions.
Okay.
Yeah, so the first question is, or we have 4 questions. How do you recommend modeling a 3-flange assembly with threads in flange 3, a washer on the outside of flange 1, and only a through hole in flange 2? I hope I said those.
Yeah, that's the additional. A single shear is relatively straightforward when you have just 2 members, and but as soon as you start getting to 3 members, and especially have different thicknesses and different moduli, then what stiffnesses do you use? You may actually end up with different stiffnesses because you'll have multiple elements representing a fastener. As far as if you have just a through hole with no clamp up at all, that's complicated because it is probably going to elongate, and you don't have that head fixity, so you're not necessarily going to translate a moment. So I'd probably still use one of these stiffness calculation methods for the fastener. But if there's no clamp up on one side, if it's just a pin through a hole, then I would probably leave the degree of freedom there free to rotate. The rotational degrees of freedom, I'd leave them free. At least that's the best I can think of off the top of my head, unless someone else has another alternative, but that's what I would probably end up doing.
And our next question is, when we tried fastening a solid mesh to a plate mesh with beams RBE2, spiders, contact, and preload, the plates kept ending up inside the solids and not by an amount attributable to rounding or display errors. Is there a way to prevent that, or is the solution to avoid modeling 2D to 3D contact plus preload joints?
Yeah, well, so that kind of surprises me because contact should prevent them from passing through each other. Now, when you do contact between 2D elements, you have a couple of different options inside FEMAP for defining that. One option says include the effect of thickness and offset on the contact. In other words, Nastran will calculate in physical space where the upper surface of your 2D element should be, and ensure that that contact then occurs there. If you don't turn that option on, then it's going to perceive the fact that assuming you've modeled it at a midplane, it's going to perceive that as being a gap, and it's going to close that gap. So I don't know if that makes sense, but if you go under connections properties here, do this on the fly without messing it up. So in this case, say linear contact, include shell thickness. If you do not turn this on, and you also have the option to include an offset. If you don't turn this on, then yes, it will perceive the difference between the mid surface and the upper surface of your shell as being a gap and close it. So maybe that's what you're seeing. Without looking at your model, it's hard to say. That would be a thing where you can contact Saratech support line, and they can look at it for you and see if they can give you some suggestions.
Perfect. And then the next question is, element perpendicular to plate is a K6 ROT issue. Can the CFAST use more than one element per side?
Yes, it can use as many elements as you want. Well, I take that back. It's basically on the diameter. So it's typically, depending on your mesh size, it's going to grab one element. But if you mesh it fine, it'll grab multiple elements. And yes, that's a good point, because you don't have that stiffness and drilling degree of freedom. And if you have an element that's normal to it, then you run the risk of it having a singularity and rotating. One of the interesting things I forgot to mention about the CFAST is it actually figures out what the axial direction of the fastener is automatically by looking at the local normal of the elements and creating a coordinate system. So even if you had coincident nodes for your CFAST, it would still create an axial direction for you automatically. But you notice when you look at the model that I created and you look at the CFAST, it actually is connecting out to multiple nodes here. So you shouldn't, I don't think, have an issue with a rotational singularity here. It should be stabilized by the fact that it's actually connected to multiple nodes. So if you are having a problem, again, give Saratech support a call, and they can help you figure out why. Because I wouldn't expect with the CFAST that you would have that problem. That's, again, one of the advantages, I think, of using a CFAST is it actually is going to behave maybe a little bit more stably, and it's going to spread the load out a little bit better.
And the next question is there an advantage or disadvantage to using beam elements instead of using bar elements for the fastener between the RBEs?
Good question. Bars versus beams. So I tend to go to a beam element in general. Why? Because beam element has more options. So even if I'm not using those options, things like tapering and so forth, I still have the ability to just modify the property if I want to turn any of those options on. And then I'm going to have you picking beam elements just because if I do a nonlinear analysis, bars are not a nonlinear element, whereas a beam is a nonlinear element. So even if I don't anticipate doing a nonlinear analysis, I think it's a good idea just to use beams in case at some point I decide to run something nonlinear. My beams are already in there, and I don't have to worry about changing them, or I don't forget to change them. And I really don't know of any disadvantage to using a beam over a bar. Computationally, I don't think it's any harder. In the end, it comes down to stiffnesses and degrees of freedom. And so there may be a tiny amount of extra computation required for creating the element matrices for the beams. But the amount of time it spends creating a bar element matrix versus a beam element matrix is trivial. Literally it's in milliseconds. So I think just as a general rule, I just default to using beams for everything.
And in the CFAST elements, why did we not choose all the plate elements connected to the fastener location?
Good question. So there's so let's talk about that. I appreciate that question. So we could do that. So remember, we're connecting patches together. And so in this case, I define the patches as being a pair of elements. So only one element per patch. What I could have done, and that would probably make for an interesting demonstration too, I just didn't need to do it, is I could have put all of the elements in this top sheet in one property region, all of the elements in this bottom sheet into a different property region, and used those property regions as my patches, in which case then I could potentially attach all of these elements together, not just a pair of elements. And what Nastran would have done is it would have taken this node location, or the node I used to define the location, and it would have projected it onto each patch. And then based on the diameter of the fastener, it would have picked which elements to connect automatically. And given the mesh size I chose and the fact that my fastener is, on par with being the size of an element, it probably would have grabbed all 4 of these and connected them together. And that's, again, the beauty of it is it would have done that more or less automatically for me. So you're absolutely right. I chose to just connect pairs of elements together, but there's really no reason I couldn't have told it to do it based on a property patch, and it would have automatically grabbed 4 elements around the fastener location to connect together. I hope that answered your question.
Awesome, thank you. And then this question I can answer. It's, can you send the slides out so that we have live hyperlinks to the further reading documents? And I will go ahead and send the slides out to everyone who has joined our session today. And then we have one more question for you, Derek. We tend to ignore the moment contributions recovered when post-processing fastener loads, tension, and 2 shears with a 6 DOF stiffness CBUSH. Is that conservative?
Yes, I think it is. And that's, again, why I said I don't think it's really all that important whether you have a zero-length fastener or not, even though separating it's going to cause a moment. Those moments and the resulting stresses are fictitious and they're going to be ignored anyway. So I think what you're doing is probably just fine. All you really want to figure out is what's the axial load, what's the shear load coming out of the fastener, so you can go off and do your calculations for bearing and net section and so forth. And the moments themselves are kind of fictitious. And in theory, as long as things are being clamped together sufficiently over a large enough area, you're not going to be seeing moments there anyway. It's all going to be, you might get some heel-toe effects if you're talking about maybe a flange, but there are hand calcs to account for a heel-toe prying effect for fastener and tension. So again, you don't need that from the finite element model. That's generally going to come from the hand calc as long as you get a good axial load on your fastener. So yeah, I think that's fine. These are just things that I know are available on the web. I threw the last one in there just because we do get questions on the Rutman method. And so that's the paper, although I don't think, when I did a quick search online, I couldn't find a publicly available PDF unless you're an SAE member. So I don't have a hyperlink for that one. And some of these others just give you, kind of an idea of recommendations for joint design and analysis and how load gets transferred in joints. So you might find some of these useful.
Thanks for checking out our channel. If you like what you saw, make sure to like and subscribe down below so you don't miss out on any new videos. Follow us on LinkedIn, Facebook, and Twitter for the latest engineering news and information. And to see all of our upcoming events, please visit our website at saratech.com/events.